Hello everyone, and welcome to this video on solving problems using the Pythagorean Theorem. So in this video I just want to talk about what the Pythagorean Theorem states, and I'll go over one simple example involving a right triangle and use of the Pythagorean Theorem, and then a little more complicated word problem where the use of a right triangle will help us to approximate a distance. So let me begin. My first page is going to simply be about, the Pythagorean theorem. Alright, so this is a theorem, a statement about right triangles only. So here's a very rough picture of a right triangle, right? So it's got three sides, right? And what makes it a right triangle is that two of those sides form a 90-degree angle. This is 90 degrees here again, usually just indicated by a little box symbol like that. So this is a right triangle. All right. The two sides, there's some special names you're going to need to know. The two sides that form the 90-degree angle, so this side here and this side here, are called the legs of the triangle. So I'll say that this side is leg 1, leg 1, leg 1 going up and down here. And then this other side that also forms the 90-degree angle, it's leg 2. Right. And then this other side that doesn't form the 90-degree angle, right, or the side that's opposite the 90-degree angle, also the longest side of the triangle, because it's opposite the largest angle. This is called the hypotenuse in a right triangle, right? The side opposite the 90-degree angle, hypotenuse. All right. So what the Pythagorean theorem states is that is just this: in a right triangle, all right, in a right triangle only, the sum of the squares of the legs, right? So if I take the length of, say, leg 1 in my picture and square it, and then add to this the length of the other leg, right? So leg 2, and square that, the sum of the squares of the legs will be equal to the square of the hypotenuse, right? So whatever the length of this longest side is, right, the side opposite the 90-degree angle, the hypotenuse, that length squared. All right, so this is the Pythagorean theorem, right? A statement about right triangles only. All right, and very often you're going to see in texts the lengths of the legs. Right, so here's another right triangle, say, right, with the 90-degree angle, say there, formed by these two sides. Very often in a lot of textbooks you're going to see the lengths of the legs labeled as a lowercase a, right? This leg has a length, leg 1 has a length of lowercase a units, and the other leg referred to as, very often as a lowercase b, right? So this other leg, leg 2, has a length of b units. And then the hypotenuse, right, opposite the 90-degree angle, is very often symbolized by a lowercase c, right? So this is a length of c units, And then by the Pythagorean theorem, the sum of the squares of the legs, right? So a squared plus b squared will be equal to the square of the hypotenuse, right? Will be equal to c squared. All right, so very often you're seeing that formula show up in textbooks, but just know this, that they don't always have to be labeled A, B, and C. All right, so that's why I like it up here where it's just a leg squared plus the other leg squared is equal to the hypotenuse squared. All right, so now I'm going to get into some examples where this is going to be used, and one of them will be a very simple problem and the other one will be a little more complicated word problem. All right, so the first one is just this simple example here. I have the lengths of the legs, right? The legs of a right triangle are given. Then I'm asked to find the length of the hypotenuse, right? The longest side, that side opposite the 90-degree angle. And if you'd like, I know that I have a right triangle here. I can draw a little diagram, a little picture. Here's a very simple looking right triangle. Just mark that off as a 90-degree angle there with the little box. And we're given the lengths of the legs here, right? Little a, like I said, usually represents the length of a leg, right? So let's say this side here, right? Again, the two sides that form the 90-degree angle are the legs. Let's say this leg here is the one that has a length of 3 units. 3 units long, 3 inches or 3 miles or something, whatever the units are. And then the other leg, right, the lowercase b, right, they told us these were the legs, is 4 units long. Alright, so if this is 3 inches, that's 4 inches. Or if this is 3 miles, that's 4 miles, as long as they'd be consistent with each other, right, have the same units. And what we're asked to find is the length of the hypotenuse. Now you could call this thing the hypotenuse and write out the word hypotenuse over here, but like I mentioned before, very often if they're using A and B for the legs, we'll call the hypotenuse little c. Alright, so then by the Pythagorean theorem, if you know 2 side lengths of a right triangle, you can use the Pythagorean theorem to find the third. Because when you use the Pythagorean theorem, what you're actually setting up is a quadratic equation, right? You're going to have something with a variable squared, and then solve for that variable. So by the Pythagorean theorem, right, we would have the length of one leg squared, so 3 squared, plus the length of the other leg squared, 4 squared, should be equal to the length of the hypotenuse, c squared, right? So the sum of the squares of the legs is equal to the square of the hypotenuse. And you see how we have here a quadratic equation? Right, I'll write that here. Because you have a variable squared, right, c squared, and there's no other c to the third or c to the fourth, that's the highest power on c here. So they would say that this is a quadratic, quadratic in c, right, in that variable c. And then we'll solve this. Alright, so we have I'm going to switch the sides here. So we'll have c squared on one side. I'm just taking it from the right side to the left side, and then 3 squared is 9 plus 4 squared is 16. So we have c squared equals 9 plus 16 is 25. And then we have to solve this equation. Now remember the square root property for solving quadratic equations brought up in a prior video. Remember, by the square root property, and if you're not familiar with the square root property, look up a video on it or one of my prior videos on using the square root property. Now here I have a variable squared equal to some number. Right? When that happens, by the square root property, this base, the c, is either going to be could either be the positive square root of 25, right? The positive square root of that number, or the value of c, that base, could be the opposite of that, negative square root of 25. And we'll simplify the radicals here. The square root of 25 is simply 5, right? That's the non-negative square root whenever you see that symbol. So c equals 5, or c equals negative 5. And then, as with any equation or any word problem, any problem at all, always check your solutions. Now, they both work in this equation, the way it originally looked, or this equation here. 5 squared is indeed 25. Negative 5 squared is indeed 25. So they both work, but think about what we had here back in the beginning, right? We're talking about a triangle, right? We're talking about lengths, right? Talking about lengths. And when you talk about the length of some segment, right, length should be non-negative. All right, so because we're talking about, the length of a side of a triangle, I'm going to say that this non-negative solution is no good, right? Again, since length should be non-negative. That is the only reason I'm eliminating that, right? It worked back in the equation I wrote, but it doesn't make sense for the particular problem. So the length of the hypotenuse is this other length here, positive 5 units. And there it is, right? The length of the hypotenuse, positive 5. If you want to put it back in the diagram here, there you go. And 3 squared plus 4 squared is indeed 5 squared. Right? Pythagorean theorem holds. Okay, great. Alright, so that was one pretty relatively simple example, right? You're given the lengths of 2 sides of the right triangle and asked to find the third side. The next one's a little trickier, involves a little more geometry. Right, so I'm going to hopefully refresh your memory if you've taken a geometry course before. I want to point out one thing that you should remember for this next problem. All right. So just a recall on a couple things. So say I have a circle, right? This isn't a perfect circle or anything, but what a circle is. A circle has a center, right? A point at its center, and then every single point on the circle is the same distance from this center, right? So this point here, this distance and this distance should be the same, right? Little tick marks to show that they're the same. And that distance, right? And again, even this distance down here, right? All the same, all the way around. No matter what point you go to from the center, you're traveling the same distance. This distance is called, the radius of the circle. R-A-D-I-U-S. Radius. Right, and that's the distance from the center, to any point on the circle. All right. Now, if I take a point on a circle and draw a line that only touches that point, it doesn't cut through the circle in 2 points, right? So like if I think of my pen here as a line, right? This one cuts through the circle. That's not what I'm talking about. This one cuts through the circle. This one cuts through the circle. If you draw a line that doesn't cut through the circle but only touches at that one point. So say I do that up here. Right? Here's a line, perfectly straight line, right? I probably should have used a ruler, sorry. I draw a straight line that touches only at one point on the circle. That is called a tangent line to the circle. Right? Or they say it's tangent to the circle. Well, the beautiful thing is, and again, my drawing isn't wonderful, so I'm going to use some notation. If you have a circle and you draw a tangent line to that circle, right, a line that only touches that circle at one point, the tangent line will be perpendicular to a radius at that point. Right? Here's the radius at that point, right, from the point to the center of the circle, and then the tangent line, they will form a 90-degree angle, the tangent line and the radius. All right, so I'll make that little note off to the side here. So a tangent line to a circle is, perpendicular. And again, this is just a fancy word for forms a 90-degree angle, is perpendicular to a radius of that circle. Like I'm seeing up here. All right, again, little box notation for 90 degrees. All right, so we're going to have to keep that concept in mind when I talk about this next problem, where we're going to end up using the Pythagorean Theorem. Okay. So I pulled this from some intermediate algebra textbook. So bear with the length here. A little word problem. So the first, just a bit of information. The USS Constitution, aka Old Ironsides, is perhaps the most famous ship from United States naval history. And if you'd like to learn more, look it up. Google the USS Constitution, Google Old Ironsides, and read about it if you want. The main mast of the Constitution, the USS Constitution, is 220 feet high. Alright, so a little bit of information about the ship. Then we have this. Here's the problem. Suppose that a sailor climbs the main mast to a height of 200 feet in order to look for enemy ships or enemy vessels. How far could the sailor see? And look at this. We're assuming the radius of the Earth, the entire world. We're assuming that the radius is, about 3,960 miles. Alright, so I'm going to draw a little picture here. Okay. So we're going to make a lot of assumptions here, just so we can get nice approximations for this problem. So I'm going to assume that the Earth is, perfectly circular or perfectly spherical. It's not exactly. It's actually what they call an oblate spheroid. Again, you can Google that too if you want, but we're going to assume that the Earth is, perfectly spherical. All right, so suppose that this is the Earth, right, and it has a radius of 3,960 miles. So from the center of the Earth to the surface of the Earth, about 3,960 miles. Okay. So what's being said here is that I'm on a ship. Now this is a giant ship. This is the mast of my ship, right? The main mast. And they're saying the sailor, right, climbs up 200 feet. All right, so this little distance I just drew here, let's say that's 200 feet. All right, the sailor. So here's the sailor at the top, and he looks out. Now, when you look out, if you ever go outside, when you look out, the farthest you can see is to the horizon. Right? No matter how high you are, the farthest you can see is to the horizon, and that's where the Earth, starts curving away from you. So if this sailor looks out, the furthest the sailor is going to see, let's say this is the sight of the sailor here, is to where it curves away. Right? So the sailor is looking away. Right, I'm not looking out into space, because if I look this way, it's just going out into space forever. I'm still looking out toward the horizon, right? So this point right here, let's say, is the horizon for this sailor, right? And if I were to continue that, that's basically where your sight line touches the Earth at one point. And if you were to continue that, then it's going out into nothing. This is a tangent line, right? Your line of sight, when you look out at the horizon, is actually a line tangent to the Earth. Touches, at that point where the sky meets the Earth, where the sky meets the surface, at that one point, your line of sight is forming a tangent line to the surface of the Earth. So, remember what I said on the last page. There's the line of sight. Here's the center of this circular Earth. Remember, your line of sight is a tangent line. Your line of sight to the horizon is a tangent line to the Earth. And if I drew a radius, all right, this is a radius of 3,960 miles. Remember what I said last page, that this tangent line and this radius are going to be perpendicular. They're going to form a 90-degree angle. All right, and can you see the right triangle coming out of this? All right, I'll draw a bigger version of this on the next page. But if I draw this, if you go from where the sailor is standing on this ship, right, he's 200 feet up off the surface of the Earth, off this mast, if you just draw a segment from the sailor straight down to the center of the Earth, you create this other radius right here, another 3,960 miles. All right. Do you see the right triangle? I know it's kind of tiny. I'm going to draw it a little bigger on the next page. But there's a right angle formed by your line of sight and then the radius of the Earth. And then you have the radius of the Earth directly beneath the sailor, and then that mast that the sailor is also standing on, a little extra length there. You create this right triangle. All right, so I'm going to draw that right triangle one more time, a little bigger, on the next page. All right, so I'll keep it up here. So here's the right triangle in question. So we have the 90-degree angle. Right, one of these legs was just the radius of the Earth. So let's say this leg is the radius of the Earth. That's 3,960 miles. The other leg, right, was basically the answer to the question. Right? The question was, how far could the sailor see, out to the horizon? What's the furthest he could see out? So from the sailor to this point here at the horizon, that's how far the sailor can see. So let me call that something, right? Just like any word problem. I'm going to call this, x miles. Let's just keep, let's just keep everything in miles, where x is, how far the sailor can see. And then the hypotenuse, right, the side opposite the 90-degree angle, the hypotenuse of this triangle is, the radius of the Earth underneath where the sailor is, plus, how far off the surface the sailor is on this mast. So the hypotenuse has a length of 3,960 miles plus an extra 200 feet. All right, and this is going to cause a problem here. Remember, and I'm sure you've seen word problems in the past. Right, we want units to be consistent. I want consistent units throughout a problem. So, miles, miles, miles. Feet. I'm not gonna keep writing this as well, right? I would like everything. I've already got 3 other things in miles. I'm gonna change this 200 feet to miles. So make sure, be sure to have consistent units. Okay, so let's do that here. We'll do a little conversion. That 200 feet, that's a problem. I want to change this to miles, so we're going to multiply. Now hopefully you recall how to do unit conversion. I want to multiply by 1, right? I want the numerator and denominator of the thing I'm multiplying by to be the same value, so that way I'm multiplying by 1 and not actually changing the value of 200 feet. But I would like feet to go away, right? So if I have feet in the numerator of this fraction, right, this is like 200 over 1. I would like to put feet in the denominator of what I multiply by. That way feet will, unit cancel. And we're trying to change it to miles. Right, miles. So I want miles in the numerator. And what I'm going to do is I'm going to make sure I have the numerator and denominator are actually the same value. Alright, so again, that way it's like I'm multiplying by 1. So what's the conversion from feet to miles or miles to feet? Well, 1 mile, right? So 1 in the numerator. 1 mile is equivalent to 5,280 feet. 5,280 feet. So I have 1 mile in the numerator, 5,280 feet in the denominator. That way they're exactly the same. And this is like multiplying by 1. Alright, and we can simplify this a bit. Alright. So you see the feet will cancel, right? And what I'm left with is 200 times 1 in the numerator, 200 over, and then 5,280 in the denominator. And this is how many miles 200 feet is, right? So it's 200, 5,280ths of a mile. Now, of course, we can simplify this fraction a bit. They both have clearly a factor of 10 in common. So I can get rid of those zeros at the end, divide out a factor of 10. So that'd be 20 in the numerator, and then 528 in the denominator, miles, right? That fraction of a mile. But also, they're both even, these numbers, 20 and 528. So 2 goes into them evenly. In fact, 4 will go into these evenly. This is 4 times 5, so I'd have 5 left over when I divide out of 4. And this would be, 4 goes into this 132 times. Alright, so this is 5 over 132. So that's actually what I'm going to change this to. Instead of 200 feet, I'm going to change it to 5 132nds of a mile. Right. That way everything's in miles. Right. Okay. Now that I've done that, got all my units consistent, let's solve for x. Right. I want to find how far did the sailor see. Right. How far could he see 200 feet up that mast? So by the Pythagorean Theorem, right, the value of one leg. Now, again, since everything's in miles now, I'm not going to keep writing the word miles anymore, because I know everything is in miles. All right, that's clear to me now. All right, so one leg squared, so 3,960 miles squared. So make that square miles, plus the length of the other leg, right, the other length that forms the 90-degree angle, the x miles squared, that's going to be equal to this other side. I'm going to write as a sum. Right? We have 3,960 miles, plus this, 5 1/32 of a mile. Right? That's how many miles. Let's ignore all this stuff now. Get rid of that. Right? Ignore all this. We changed 200 feet to miles already. So this plus this, that's how long the hypotenuse is. And then we're squaring that. All right. Okay. So, I'm going to, because these numbers are pretty large, I'm actually going to go about using a calculator here. All right. Nothing wrong with that when the numbers get too gaudy. So what I have on the left side, right, 3,960 squared is a very large number. Right? So on the left side, that's 15,681,600. Right? That's 3,960 squared. All right, plus, and then x squared equals, then again I'm just going to go to a calculator, and in parentheses, I'll put up what I'm doing here actually. All right. In parentheses, I got the length of the hypotenuse was that 3,960 plus, and then 5 over 132, and then we're taking that quantity and squaring it. All right, and some it's a nice large number as well. All right, it's 15 million. Oh, so this will actually end up okay. Look at this. This is 15,681,900. So this is beautiful. All right, when I get x squared alone, right, I want to solve this using that square root property. Right, I got a variable and a square, and no variable outside that square. I would just want to get x squared alone, so I'd subtract this number here. Well, if I subtract this, notice they're the same up until the last 3 digits. So really you're just doing 900 minus 600. You get x squared equals 300. Right? So x could be equal to, by that square root property. If x squared is 300, x could be the square root of 300, or x could be the opposite of that, right? The negative square root of 300. But like I mentioned earlier, we're talking about length here. The question was, how far could the sailor see? So not going to count this one with the negative answer. Again, because we're talking about distance, we're talking about length. Right? That's why I'm Xing out the negative square root of 300. All right, and then of course I'd like to simplify this radical. Now the square root of 300, 100 is a perfect square, right? 10 squared, that goes into 300. I could break this down to the square root of 100 times the square root of 3, right, using that product property for radicals. And that would be 10 times the square root of 3. Right? And if you want, I'll approximate this. I'm going to punch this in a calculator. All right, what's 10 times the square root of 3? It's about 17.32. All right, notice I'm using approximately, and I'm going to nearest tenth, nearest hundredth, whatever you feel like. Great. And of course check the solution, and this should work back in the original equation. I don't think I did anything wrong. But of course check it, right? I'll never forget to write that. Don't forget to write that down. Check your answers, of course. That should work for this equation, or the original equation I wrote even. Okay, so now I have to answer the question. Right? Sure, we solved the equation, but we have to answer the question, and I've mentioned this in other videos of mine as well. When you have a word problem, you should be answering your questions in complete sentences and have units attached to the numbers so that they give them meaning. All right, what was the question here? What did they want? What did they ask of us? How far could the sailor see? And notice I solved for x down here, and what did we say x was earlier? X was how far the sailor could see, and I made sure everything was in miles, right? So this is in miles. So the way I would answer this question, if I were given it on a test or a quiz or some sort of homework assignment, how far could the sailor see? The answer, a full sentence. The sailor could see, and then, what was x here? Now you can write the exact answer, 10 times the square root of 3 miles, right? Every number should have a unit on it to give it meaning. Or approximately, right, what does that mean, that number? Or approximately, 17.32 miles. All right, but just a little over 17 miles away the sailor could see. And this is how I would actually write the answer to this question, right? Not just a number. It is a word problem, an application problem. You should be writing complete sentences with the units on the numbers to give them meaning, please. All right. Yeah, so this one was a bit tricky. This one involved the use of a couple of assumptions here, right? We assume that the Earth was a perfect circle, which it really isn't. Again, look up oblate spheroid, O-B-L-A-T-E, and then spheroid, S-P-H-E-R-O-I-D. But we assume the Earth was a perfect sphere, right? Perfectly circular. And also we had to use and assume that the radius was about 3,960 miles, which it is about that at the equator. And then we had to bring into the notion, we had to bring in some outside knowledge, which you have to do very often in word problems. You have to bring in knowledge of outside concepts or outside formulas that you can apply to the problem. I had to bring in the knowledge that a tangent line, that my line of sight would be perpendicular to the radius of the Earth at the point on the horizon, right? At the point where my sight meets the surface at the end there at the horizon. And then, of course, we had to bring in the fact that we knew the Pythagorean Theorem, right? A right triangle did appear when that concept of perpendicular tangent to radius came in. And then go from there, right? Leg squared plus leg squared equals hypotenuse squared. So a lot of stuff involved in that. I went from a very simple example to start to a much more complicated example, but still, that just shows you, you can run the gamut. You can go from very easy to very, very difficult, very complicated, and still be using the same things over and over again. Still be using the Pythagorean theorem to solve all sorts of problems. Okay, so as I like to say at the end of these videos, do the best you can to try and learn the material on your own before you go looking for help. I have found over the years that people who tend to take the time and the effort to learn the material on their own, well, those people tend to remember the material better, and they also seem to remember it for longer, right? Not just for the moment, not just for a test, but for much longer after that. And they're more proud of themselves for it, which is also good, boosting confidence in your abilities and your belief in yourself. All right, so of course read the material. All right, read through the author's examples. Perhaps even try to work out the solutions to an author's examples before you see how the author did it, and then compare your work with the author's and see if you can learn from some mistakes there. Obviously work on tons of exercises, practice problems, because practice makes progress. The more you do something, the better you get at it. And of course, and check for solutions to those if they're made available, right? So you can see how you're doing, check your progress. And don't just give up on a problem after 1 or 2 attempts either, right? Don't give up so easily. Very often in mathematics there are several approaches that'll work for any particular problem. So, if after several approaches at a problem you're still having trouble, maybe you should go back and read the material again, maybe even a third time, more slowly, more deliberately, take good notes. Because if you've been working on some problems, like you should, there's a good chance that you have a better idea as to what the author wants from you in that particular section, what the author is expecting of you. So then when you go back and read the section again, or maybe even that third time, you'll have a better idea as to what to look out for. What you'll know more about what's important in the section if you've been asked problems about it. You've been working on questions, and things might even pop out at you, that didn't the first time through, and it'll make working on the exercises that much easier. But if after that, if after several read-throughs of the material and several attempts at problems, you're still not getting it, you're still having trouble, perhaps you should go looking for help then. Right? It is not a sign of weakness whatsoever to go asking for help. That is what other people are there for, to help you. So ask a teacher, a tutor, a friend, someone in your class who you know knows the material well and is willing to help. Look for supplemental materials online. There's tons of it out there. Look for videos online. There's loads of those too. Videos like this one, or plenty of other ones out there better than this one. I assure you they're out there and they're easy to find. But just keep at it. Stay persistent. Keep practicing. Don't give up. And above all, I think this is the hardest thing for most people, is stay positive about the subject. Believe in yourself, even through your frustrations and struggles and failures. Try to find a way to get past that. Work through it. Because if you can find a way to fix your mistakes, work through your struggles, work through your frustrations, it's in those times of struggle and failure that you can learn the most, by learning how to fix your mistakes. And you'll also learn even more deeply when you work through a struggle and a failure. You learn more through failure than you do through breezing. Right? You'll remember that material better and longer than someone who got it right the first time and then never thought about it again. They just breezed through. You'll remember it months from now when they're forgetting it a week later, because it had that emotional impact on you. So just please, stay persistent, keep practicing, stay positive, and don't give up. And I just know you'll get it. And thank you very much for watching.